but Courtney's building is doing fire alarm testing, so that would not have made the presentation very smooth. There was a lot of anxiety about that. So that's why we are where we are. Okay, I think probably everybody is ready. So let's go ahead and get started. I'd like to introduce all of you to all of you. Before you start, Courtney, okay? I'd like to welcome 4 groups of people here. First of all, our grad students. Hopefully we have some of our current grad students logged in. They would like to know what the end of the process is like, and so that's why they're here. And then hopefully we have some grad students from Courtney's cohort who have probably left now, but if you're here, welcome. I'd like to say hi to the faculty of San Jose State. As you see on the screen, Dr. Chen Tan is one of the people on Courtney's thesis committee. So hi, Chen, nice to see you. I'd like to welcome the members of the NASA Ames Mars General Circulation Modeling Group to our meeting. Courtney works out there with them, and the group is directed by the other member of Courtney's committee, Dr. Melinda Kari, who hopefully is in one of your Hollywood squares waving at you right now, but possibly not. And finally, I'd like to welcome family and friends of Courtney's to this talk. I hope you understand what she's saying because she has a lot of good stuff to talk about. So it's a great day to be a Martian. I'm wearing my NASA themed t-shirt today because there is a lander landing at about 5 to 1, we should find out. So if you see some of us going like this, that's why. The timing is great. Courtney's been doing work on a certain kind of dust storm on Mars, doing observational work and modeling work. And so you see the title there, and it's over to you, Courtney.
All right. So, hi, everyone. I'm grateful you took time out of your day to attend my defense, especially since, like Dr. Bridger said, it's T-minus 55 minutes until Perseverance lands on the Martian surface, which with any luck will be the grand finale, but certainly feels like a poetic conclusion to my graduate experience. So with that, I will be defending my thesis titled Observational Analysis and Modeling of the B Regional Dust Storm on Mars. And let's get started. So when I talk about dust storms on Mars, this is what people typically imagine. And by people, I mean my family and some of my SJSU peers too. This is Matt Damon getting wrecked at the beginning of The Martian, and it is pretty unrealistic. But I hope that by the end of my thesis, you'll have a better idea of what a dust storm on Mars is actually like. So without further ado, here's a picture of a global dust storm from 2001. These are 2 images of Mars that show what a global dust storm looks like. On the left, we have a mostly clear atmosphere with a regional sized dust storm in the Hellas Basin circled at the bottom right. And within a month, the whole planet is covered in dust. And this was the 2001 global dust storm. These have been observed from Earth since the early 20th century as just sort of a blurry Mars. And the first time a global dust storm was observed up close was in 1971 with the arrival of the Mariner 9 orbiter. It was from those data that we first understood the importance of dust in the atmosphere, that it was an excellent absorber of solar radiation, and that it could therefore significantly warm the atmosphere. So this is what a global dust storm looks like from the Martian surface. On the left, we have a GIF of photos spanning about 2 weeks from the Curiosity Mars rover. And on the right, we have a simulation of what the sky would look like in some of the dustiest parts of the storm. On the other end of the spectrum of dust activity on Mars, we have dust devils. And these are really similar to the dust devils we have on Earth. These are images from the Spirit rover at Gusev crater over about 12 minutes, which shows you just how common dust devils are on Mars. You can see 3, 4 of them coming across your screen. And these are thought to contribute significantly to maintaining the background dust layer on Mars, just the background dustiness and hazy orange sky we're used to seeing in photos. So as you can see, dust activity is really varied on Mars. And here I wanted to give you a sense of the scale of the storm that we'll be looking at today. So we've already talked about global dust storms. They cover the entire planet in dust. We also have the small dust devils, which aren't technically storms, they're just dust activity on Mars. And then somewhere in the middle, we have regional scale and local scale storms. And a regional storm has to typically cover an area of at least 1 million square miles, which is about 1/4 of this circle on the screen. That's that dust storm in Hellas Basin. And regional dust storms can be as large as almost the entire planet, but once it's planet encircling, it's a global dust storm. And regional storms have to last longer than 3 days. So any storms smaller than that or shorter than that are considered local storms. The storm that we're going to be talking about today is called the B storm. It's a regional scale dust storm, and it's located south of that Hellas Basin in that region circled at the bottom, so over the South Pole. But before diving too deep into that, I want to provide some background on the Martian atmosphere, especially compared to Earth's, since this is a Earth meteorology program. And then I'll explain the B storm, which is the subject of this thesis, and what motivated our research on that. And then I'll describe some of our observational analysis, our modeling analysis, and wrap it up with a summary of our main conclusions. So getting started with the background on the Martian atmosphere, we have Earth and Mars depicted at the top, not to scale, but sort of relatively to scale. Mars is about 1/3 of the size of Earth overall. Its radius is about half that of Earth's, a little bit bigger than half that of Earth's. And Mars is 50% further from the sun than Earth is. The main atmosphere constituent on Mars is carbon dioxide, which is obviously not the main constituent of Earth's atmosphere. Earth's atmosphere is mostly nitrogen and 20% oxygen. The Martian surface pressure is just over 6 millibars. That's 0.62% of Earth's surface pressure, which is 1,013 millibars on average. And because Mars's atmosphere is more than 100 times less massive than Earth's, its surface temperature is pretty cold, about 210 Kelvin or negative 81 degrees Fahrenheit. For context, on Earth, our surface temperatures average 287 Kelvin, or a nice balmy 57 degrees Fahrenheit. And there's no liquid water on Mars. That has important implications for the exchange of heat in the atmosphere and between the surface and the atmosphere. Mars lacks oceans, which means its surface thermal inertia is much smaller than Earth's. It takes a lot less time and energy to change the temperature of the surface or the atmosphere on Mars. It's also part of the reason dust is so effective at radiatively heating the atmosphere. And last but not least, Mars has this interesting thing called a condensing atmosphere, where a large percent of the mass of the atmosphere, in this case 25 to 30% of the mass of the atmosphere, condenses onto the surface seasonally. So Mars's atmosphere, being primarily carbon dioxide and having a low surface pressure, is near the frost point of CO2. So at the winter pole, it becomes cold enough for that CO2 to deposit directly on the surface as ice. And it creates these seasonal ice caps on Mars that I'm going to illustrate for you now. So in this video, you're seeing a simulation from our global climate model of an animation of the growing and receding seasonal ice caps at the North and South Pole. GCMs like this one are capable of capturing many aspects of the dust cycle on Mars, and they can adequately reproduce the effects of a global dust storm. Here you're seeing some dust in the dusty season. That's not a dust storm, it's just the background dust haze. It's more common in the second half of the year, known as the dusty season. These ice caps at the North and South Pole, and you see them on the left and right too, are carbon dioxide ice. The residual caps beneath them are mostly carbon dioxide ice, but also have some water ice. And with the seasonal deposition and sublimation of carbon dioxide ice at the poles, Mars's surface pressure fluctuates about 30%. So the dust cycle is that yellow haze you see in the second half of the year. And we also have some water ice clouds that develop on Mars, and you see those more in the northern summertime climate right here along the tropics. Those are water ice clouds. So again, we have Mars and Earth. There's a lot of similarities between the two, which is a big reason why we study Mars. They have similar obliquities, They differ by just 1.75 degrees, and that obliquity causes Mars to have 4 seasons like we have on Earth. And the planets rotate at almost the same rate, so the Coriolis effect operates similarly on Earth and Mars. That means geostrophic balance applies. The mid-latitude winds can be approximated by geostrophic theory, and Mars also has large-scale weather systems as a result. And here's an example of that. And these photos are the same scale, 4 kilometers per pixel, and you're seeing a dust storm in the northern hemisphere of Mars, and then a dust storm off the west coast of Africa on the bottom. As you can see, these dust storms have similar structure. They also have water ice clouds at the top of the atmosphere. And these were only taken a few months apart in 2000. So there's a lot of similarities here, primarily that these large-scale storms can occur on Mars. So for a bit of timekeeping on and seasons on Mars before I continue forward, Mars has a highly elliptical orbit, which means it's further from the sun during northern summer, which is known as the aphelion season. It's closer to the sun during the southern summer, which is the perihelion season. And during this season, the solar insolation is about 40% greater than in the opposite season. That's how much closer Mars is to the sun. And this causes more dust activity to occur. This is that dusty season, and this is when global dust storms occur, and when the B storm occurs. So the LSUB values that are down here stand for areocentric longitude, and it just refers to where Mars is in the orbit, like degrees in a circle. So starting at LSUB 0, we have southern fall. LSUB 90 is southern winter. LSUB 180 is southern spring. And LSUB 270 is southern summer. And this is the season that we're interested in. The B storm occurs right in there. 1 year on Mars is about 668 Mars days, almost 2 Earth years long. A Mars day is about 40 minutes longer than an Earth day, and it's called a sol, but I'll probably be saying days most of the time throughout this presentation. The years on Mars timekeeping is defined by a standard set by Clancy et al. In 2000, who defined Mars year 1 as the year of the first well-documented dust storm on Mars. That was in 1971, which I mentioned on the first slide. So by that convention, it is now Mars year 36, LSUB 5.1. So we are about 11 Mars days into the new Martian year. So now that we're oriented to Mars's atmosphere, I'm going to introduce the regional storm that is the subject of my thesis and explain why we were motivated to study it. So the B storm is one of 3 annually recurring regional scale dust storms on Mars. It occurs in the southern hemisphere, and is defined and described by Cass et al. In 2016 according to the warm temperatures that these storms produce at 50 pascals, which are shown here for Mars year 31. 50 pascals is about 25 kilometers above the surface for Mars. And these temperatures were retrieved over the second half of the year, that perihelion season when it's warm and dusty. And these regional storms produce temperatures greater than 200 Kelvin at 50 pascals. The A and C storms typically occur in the southern mid-latitudes. They cause dynamic warming in the northern hemisphere. But the B storm occurs south of that, and there's no dynamic warming in the northern hemisphere. But it does occur around southern summer solstice, which means that the southern hemisphere receives sunlight for all hours of the day at that season. And finally, the peak temperatures in the B storm are often the highest, not always, but about 220 Kelvin in this case for Mars year 31. The B storm occurs in any year that there isn't a global dust storm. Global dust storms are somewhat rare events, but they are global in nature, and so the A, B, and C storms haven't been observed during them. We have orbital observations dating back to Mars year 24, and so since Mars year 24, we've had to this date about 7 or 8 Mars years without a global dust storm. We've had 2 or 3 global dust storms since then. So Cass et al. Analyzed 6 non-global dust storm years, and we'll be analyzing 7. So why study the B storm in the first place? We study dust storms on Mars because we know very little about the physical processes that control the dust cycle. and the processes that trigger the growth and decay of the dust storms on Mars. We can address part of that knowledge gap by analyzing a real observable dust storm, such as the B storm. And we choose the B storm for two reasons. The first is that it has yet to be fully characterized in the literature, in part because observational data at the South Pole is pretty scarce. And the second reason is because we have the tools to study it now. We have a new NASA Ames Mars GCM that is uniquely qualified for simulating the B storm, for Mars models at least. And I'll elaborate on these motivations in the next two slides. So to the first point, the B storm has yet to be fully characterized. Observations at the pole are limited, and data from the surface of Mars comes from typically these 9 NASA landers, which are all located well north of the 70 degrees south latitude line that defines, the B storm is south of this 70 degrees south latitude line. There's some southern hemisphere landers, but as you can see, they're still pretty far north. I did circle where Perseverance is landing today, in case you were wondering. And there have been attempts to observe the southern hemisphere. They haven't really been successful. Mars 3 landed and survived all of 20 seconds. And then the Mars Polar Lander would have been cool, but crashed at the South Pole. So we don't have any observations from the surface at the South Pole, but we do have observations from orbit. And those orbital observations span about 11 Mars years, which is about 22 Earth years at this point, and it's still growing. And it was with those orbital observations that Cass et al. Defined the A, B, and C dust storms. And we use data from orbit in this research. And the second reason we study the B storm is that the new MGCM provides a unique opportunity to study it, because the new finite volume dynamical core in the Mars model from GFDL that I now understand is implemented in the GFS model as well. It has a cube sphere grid, which you see on the left of this picture. It provides uniform spatial coverage, more uniform than the traditional grid, which is a latitude-longitude grid shown on the right. And in traditional models, it's often hard to model polar phenomena because the meridians converge at the poles, causing numerical instabilities, and addressing those can be problematic in themselves because they can introduce errors into the actual transported dust field and things like that. So the cube sphere grid is great because it eliminates that issue. So we're studying the B storm to try to address some of the unknowns about dust storms, mostly, namely what processes facilitate the growth and decay of dust storms on Mars. To that end, we narrowed our focus on 2 guiding questions. The first being, what are the mechanisms lofting dust in the B storm, and what are the mechanisms lifting dust in the B storm? And we highlight the difference between lifting and lofting here because I refer to them a lot throughout the presentation. So I have this little diagram, and you can see lifting is the process of raising dust from the surface, putting it into the atmosphere. And lofting is the process of raising dust that's already in the atmosphere higher into the atmosphere. So I'm gonna go through our plan here, and lifting and lofting require reproducing the B storm in the model because, like I said, there's limited observations at the poles, and the observations we do have, the wind observations in particular, are pretty limited. So we first need to understand what the B storm is, and we're gonna fully characterize the observed structure of the B storm, which includes extending that analysis through Mars year 33, taking a look at the vertical temperature and dust distribution, and defining the phases of the B storm evolution. And then we'll use what we learned there and put it into the model to try to reproduce the B storm in the model so that we can address the questions of dust lifting and lofting. So I'm going to get right into the observations here. I'm going to start by describing what we've observed from the B storm from orbit by describing some of those orbiters. And our orbital observations come from 2 instruments. The first is a thermal emission spectrometer, which is on board Mars Global Surveyor, and that was operational from Mars year 24 to Mars year 27. The second instrument is Mars Climate Sounder on board Mars Reconnaissance Orbiter, and that's been operational since Mars year 27. These are polar orbiting satellites. They observe the same location on the surface 2 times a day, once at night, once during the day. And TESS received vertical profiles of temperature at 10-kilometer resolution, and then MCS updated that and retrieved vertical profiles of temperature and dust every 5 kilometers. And of the 11 Mars years of data available from orbit, the B storm occurred in 7 of them, and we're going to look at those. So this is a lot of data on one screen. Just bear with me for a second. This is daytime 50 Pascal, which is, remember, 25 kilometers, temperatures over about 60 days around southern summer solstice. And this is looking straight at the South Pole. And so each row is a Mars year. We have each of those 7 Mars years shown here. And each column is about 15-day increments between observations. And the diverging color bar on the right highlights the 200 Kelvin isotherm, which David Cass used to define the B storm a few years ago. So we can see that the warmest temperatures occur consistently at this peak intensity point, which is just before southern summer solstice, except in Mars year 29, when a late season A storm really weakened the B storm. Since our goal is to characterize the B storm in general, though, I'm just going to show and describe the phases of the storm based on the Mars year 31 observations. And I picked Mars year 31 because we used dust retrievals from that year to drive the model, which I'll explain later. So this is just the Mars year 31 data. And what you can see a little more clearly now is that there's a squiggle in the middle of the plots, and that represents the cap edge, the seasonal carbon dioxide cap edge as observed. And it's sublimating away at this season, which you're seeing by it, shrinking in time. So what we can see is that during the growth phase, the B storm develops rather quickly. Temperatures poleward of 60 degrees south increase by about 10 Kelvin in those first 15 days during the growth phase. At peak intensity, which is L sub S 267, just 3 degrees before the peak southern summer solstice season, 50 Pascal temperatures are maximized over the pole at about 220 Kelvin. Maximum dayside temperatures are 220 Kelvin. And this is, again, just before solstice. And during the decay of the B storm, which occurs a little bit more slowly than the onset period, the atmosphere cools quickly initially, but then this polar region stays warm above 200 Kelvin for several degrees of L sub S after that. And overall, we can see that the daytime temperatures are warmer than the nighttime temperatures, which sounds a bit obvious and redundant, but remember that the sun is up full time, doesn't set at all at this time of year during the B storm. So that might be something that's unusual. Taking a look at the dust mixing ratios, also at 50 Pascals, 25 kilometers above the surface. And again, the daytime retrievals, nighttime retrievals, 15 days apart. We see that 50 Pascal dust mixing ratios consistently exceed 4 parts per million. If you take a look at this color bar on the right. And the 50 Pascal dust field shows higher concentrations of dust at night and not during the day, which is opposite what we saw in the temperature fields. And kind of interesting, you would maybe expect some of the radiative heating of the dust to produce greater nighttime temperatures, something like that. So at the end of the growth phase, we can see that the dust tends to concentrate in this half of the hemisphere between 45 degrees east and 135 degrees west. This is the hemisphere opposite the seasonal cap, which you can kind of see. The cap is leaning toward the opposite hemisphere here. It sublimates asymmetrically around the pole, largely because the residual cap beneath it is off center, and that sort of pulls this cap away from the center as it sublimates away. The maximum dust mixing ratios are found at the end of the growth phase at L sub S 257. Those are about 18 parts per million at maximum there. And the background dust haze, which is shown in L sub S 287, is more like 1-2 parts per million. So it's quite dusty. At peak intensity, dust is more evenly distributed around the South Pole rather than concentrated in that eastern hemisphere. Peak dust mixing ratios are about 8 parts per million. And then after that, about half the dust falls out every 10 L sub S after peak intensity, or every 15 days after peak intensity. So finally, I want to take a look at the observations in the vertical. These are distributions of temperature and dust during the Mars year 31 B storm at the same increments as before, but these are cross sections that show the surface at the bottom, 15 Pascals at the top, and we're mostly interested in what's happening below 50 Pascals between the surface and 50 Pascals. So The South Pole is in the middle, and before I go too deep into explaining this, I want to show you what you're looking at. These are not snapshots of the South Pole. They're actually two observations stitched together. So I have observations on the night from the night side on the left, observations from the day side retrievals on the right. And I do this because it sort of mimics the orbital path of the satellite as it crosses from, a night side to a day side. And we can look at comparing night side and day side column features. So we're looking at this 50 Pascal level and what's happening below there. We can see that it is typically warmer throughout the column on the day side, not just at 50 Pascals, but throughout the entire column. And additionally, the mid-latitude B storm originates in the southern mid-latitudes, and it travels south as the column grows deeper, dustier, and warmer. At peak intensity, the column is centered over the South Pole. 50 Pascal dust mixing ratios are greater than 4 parts per million, which I mentioned earlier, and temperatures are well above 200 Kelvin. And during the decay phase, dust settles out over the pole and temperatures fall accordingly. So it doesn't travel away, it just falls out over the pole. So a quick summary of these key features that we've observed. The south polar propagation of the B storm dust is there. 50 Pascal temperatures are greater than 200 Kelvin. Dust mixing ratios are greater than 4 parts per million. And the B storm peaks just before solstice, but not at solstice and not after. So recall that the goal of modeling the B storm is to be able to identify the mechanisms of dust lifting and lofting in the storm, which we can't do with observations. So we take these key characteristics and we're looking for the model to reproduce those so that we can diagnose dust lifting and lofting. So now I'm going to take you through the modeling piece. This is simulating the B storm. And so I'm going to give you a brief overview of the model first. We already covered how the new MGCM avoids the converging meridian problem with having these uniform tiles. But the new MGCM is also a highly parallelized model, which means it can run high resolution much faster than these lat-long grid models. So at the right, I'm going to illustrate some of these differences in resolution. The old model we typically ran at 5 by 6 degree resolution, which meant each of those grid spaces are 300 kilometers by 360 kilometers big. So any feature smaller than that wasn't explicitly resolved. And the new model can run as high as 1/16 of a degree resolution, which we've done. But here I'm showing you a 1/4 degree resolution, which is 15 kilometers by 15 kilometers per grid point. For this project, we ran at 1 degree resolution, which is 60 kilometers by 60 kilometers resolution. It took me about 18 hours to run the model at that resolution for 2 years and get 2 years of data out of it. For reference, if we ran the old model at 1 degree resolution for 2 Mars years, it would take several weeks to finish the simulation. So this is a major step up for us. Many of the physics packages that we developed for the old model at the Mars Climate Modeling Center are in the new MGCM and still being implemented. We have surface topography, surface thermal inertia, and surface albedo maps that are fixed quantities and read into the model. We have seasonal carbon dioxide caps that you saw earlier, growing and receding in the model. They're determined in part by their albedo, and the south polar cap albedo is usually 0.51 because this produces global average surface pressures comparable to the Viking observations. The planetary boundary layer predicts winds and temperatures for the lowest scale height in the atmosphere. Only dust and CO2 are the radiatively active constituents in our simulation. You could also have water vapor as a radiatively active constituent, but we do not let water vapor condense into ice clouds in our model because that would remove dust from the atmosphere. Dust tends to act as ice nuclei. And there are no clouds at the South Pole anyway, so we don't want to have that interfering with our analysis. So water ice clouds are turned off, and the dust scheme has a lifting scheme where we define an effective radius of 3 microns, effective radius being an area-weighted mean radius of the dust. It describes the distribution of dust particle sizes that we lift from the surface and put into the atmosphere. Once the dust is lifted, it's allowed to be sedimented out due to gravity and transported by the model winds. and that will naturally, more or less, change the dust distribution throughout the atmosphere on its own. And dust is lifted according to a map tracking scheme that I will explain more in a couple slides. First, I want to show you how the model does overall. So the model does pretty well overall. Here I'm showing zonal mean temperatures with height, and these are like those cross sections I showed earlier, but this is with the South Pole on the left, the North Pole on the right. The simulation is shown on top and the observations are on the bottom. The equator is right through the middle. So we're looking at temperatures with height, zonally averaged, and some of the key features of the southern summer season that the model captures are this pole-to-pole temperature gradient, where it's coldest at the North Pole, warmest at the South Pole, that this thermal gradient is largest in the Northern Hemisphere and produces really strong zonal winds above that, and the so-called warm tongue in the Winter Hemisphere, which is this warm feature above 4-scale heights in the Western Hemisphere that tilts toward the North Pole and is warmer over the cold pool below it. And so I want to look a little bit at some of the same types of plots I had from the observations to see how the model reproduces the B-storm. And on the left, we have those key characteristics we're looking for. And on the right, we have the kind of observed modeled fields that look like the observed fields from before. So we have 50 Pascal temperatures over 60 days, 15 days between each of the rows or the columns here, daytime temperatures on top, nighttime temperatures on the bottom, and the observed cap edge is shown again. Not the model simulated cap edge, but the observed cap edge. So we can see that the day side is warmer than the night side, as observed, that the B-storm peaks before solstice, the same time, Alcebest 267 as observed, and that temperatures exceed 200 Kelvin during this peak intensity period. Looking at the dust field, we can also see that the dust field is greater than 4 parts per million south of 70 or 80 degrees south at the end of the growth phase and during peak intensity, which is good. We can see that it's dustier at night than during the day at the South Pole, not in these mid-latitudes, but at the South Pole, where we see the B-storm. And so that is also something from the observations that the model reproduces. And looking at these vertical plots again, but this time for the model, we can see that the model captures that the B-storm is a southward propagating dust storm. We see that it peaks over the pole just before solstice, and that those temperatures are greater than 200 Kelvin, mixing ratios are greater than 4 parts per million at 50 pascals, and then dust falls out straight over the pole after that. So the model captures the B-storm pretty well. It captures the southern summer season very well. So we can start to look at answering a couple of our questions. The first I'm going to talk about is the dust lifting question, and that's raising dust from the surface. And in order to answer this question, we first need to understand how particles are lifted in the model. So I'm going to explain that. Here's how we have dust lifting working in the MGCM. So I have 2 latitude-longitude maps on the screen. They're both showing dust opacities over part of the southern hemisphere. The South Pole is at the bottom, and that ice cap observed edge is sort of outlined at the bottom too. On the left side, we have the GCM simulated dust opacities over the surface. On the right side, we have the observed dust opacities over the surface. And what's happening here is we have the GCM on the left is essentially reading in, oh my goodness, sorry, spam calls, is essentially reading in the observed map on the right, and it's putting dust into the lower atmosphere where the map indicates dust is, where and when. So if I let the model step forward in time, you can see in these shaded areas that it's lifting dust where the observations indicate dust is, and the observed map updates every few degrees of Alcebest when we have these observations available. This is important because it means that the model's not lifting dust where simulated winds are high enough to lift dust. It's lifting dust where observations say it should. This allows us to compare where the model predicts dust should be lifted to look like Mars Year 31, and where the model predicts winds are high enough to do the lifting if we let it do the lifting. And we can see if those things match or not. And if we were to recreate the actual physics of dust lifting, we would have to allow the model winds to impart stress on the surface, allow dust to be lifted right there, and allow the magnitude of that wind to determine what size particle is lifted, how much, and how high. So as you can imagine, simply allowing fully interactive dust lifting is complicated. It's just not yet part of our model, but I can take a moment to explain how dust is actually lifted in real life so we can do this analysis. So there are three ways by which particles are lifted from the surface. The first is creep, and that is just particles that are too big to be lifted, like small rocks and pebbles, are sort of blown along the surface by the wind. They creep along the surface. And then we have saltation, which is for particles about the size of beach sand. These particles are sort of lifted by the wind initially, but they're heavy and they fall out of suspension and sort of bounce along the surface. And then we have direct suspension, where really, really small dust particles, like the size of dust mites and bacteria, and dust in your home, are just lifted directly into suspension. And we do know that the average wind speed on Mars, measured at 1.5 meters from our rovers, is less than 20 meters per second. And that's too weak to do this creep process, and it's also too weak for suspension because the particles that small tend to kind of stick together. So it's actually easiest to initiate saltation on Mars. And that requires wind speeds of typically at least 10 meters per second. So we know that that's happening, but we also know that we have observed many times over that suspension is happening in the Martian atmosphere. So how is dust getting up there? There is actually another way by which dust can be lifted, and it seems like this is the primary mechanism by which dust is lifted on Mars. So we have the saltation process where these larger particles are sort of lifted and then fall back to the surface and bounce along the surface. And when these particles return to the surface, they sort of splash up these fine dust grains, which breaks up that interparticle cohesion, the stickiness, and causes them to enter into suspension. And this can happen as long as you have saltation occurring. And so we can see whether or not the model predicts saltation is occurring by looking at the surface stress field. Is there enough surface stress here to initiate the saltation process? And because dust lifting is the result of a momentum exchange between the surface and the atmosphere, we can kind of estimate that through the model. So our simulation doesn't perform fully active dust lifting yet. We have that model map tracking dust lifting scheme implemented, but we can look at where dust is being lifted by looking at these lifting rates simulated by the model, and compare it to where the model would lift dust if it were fully interactive, which is indicated by these surface stresses. And in the areas where the model predicts its surface stresses are likely high enough that dust lifting is occurring there, I've outlined those areas in black, and they're sort of these yellow and red regions. So in general, we can see that there's pretty good agreement between where the model predicts dust is being lifted and where the model predicts winds are high enough to initiate saltation. And this is throughout the growth phase and at the peak phase of the B storm, which is good. The model is lifting dust in the same area at the end of the growth phase as where these surface stresses are high enough. And there's even good agreement during peak intensity. Also good news, because that's when the B storm is peaking. And you may have already noticed that there are these blank areas sort of in the middle of these plots. And that's because the simulated seasonal CO2 cap is actually there from the model. So the colored areas in this bottom plot are where the model predicts CO2 ice is accumulating on the surface. And I have that outlined observed cap edge still there. And you can see that the observed and simulated cap edges don't align perfectly. It looks like the simulation predicts this surface ice to accumulate in a circle around the middle of the South Pole, but the retreat of the ice cap is more asymmetrical than that. So this is a limitation in our model currently, but we intend to address that in the near future. But nevertheless, what this shows is that the model is lifting dust around the cap edge, and it looks like there's cap edge lifting going on, which is not a new idea. It's actually well documented in the literature, and there are several processes that can cause it. One of those things is the sea breeze, in which warm air over the dry surface beyond the cap edge on Mars is rising, and then cold air over the ice cap is sinking, and it creates sort of this circulation that looks a lot like the sea breeze effect, where you have warm air rising over the beach, cold air sinking over the ocean, you have that nice off-ocean breeze coming in. This is evident in the literature that this circulation is strengthened near solstice on Mars, and it can produce wind speeds high enough for saltation to be occurring. And this circulation can also be augmented by or strengthened by katabatic flows, which are where dense air flows down the ice cap at nighttime, and the CO2 condensation flow, which is the seasonal mass flux of CO2 toward the winter hemisphere. At this season, it's summer in the southern hemisphere, so that CO2 is sublimating off the cap and then flowing toward the northern hemisphere and depositing back on the surface up there. And that creates somewhat of a flow. However, you can kind of tell that this is a shallow feature. 12 kilometers is just above the boundary layer on Mars, which is quite deep for Mars's boundary layer, but this is a pretty shallow circulation, and it certainly could not loft dust to 50 pascals or 25 kilometers. So we don't think that this is the lofting mechanism, and I don't think it could be anyway, because we have sinking air over the cap where we're seeing that dust. But it could be that this, it looks like our working hypothesis is that this causes the lifting at the surface, but not the lofting. So given all that, what are the mechanisms that cause lofting in the B-storm, if not the cap edge circulation? Well, you can recall that lofting is raising already airborne dust higher into the atmosphere, and we kind of know how dust is being lifted into the atmosphere initially. So to look at lofting, I'm going to show you an illustration of the hourly evolution of the dust field over 2 Mars days, 48 hours, during peak intensity. So what you're seeing here is the first hour of that 48-hour series, which will be ticked off at the top. You have dust mass mixing ratio in the background that's colored in. We have shortwave heating rates outlined in white and black. The difference between the colors is just to make the contours stand out a little bit better on the darker dust areas. And the shortwave heating rate is a measure of how much the airborne dust is absorbing solar radiation and generating heat in the atmosphere. We also have these vertical arrows that indicate, on the right, there's a legend that indicates that that size arrow is about 1 meter per second. And we're especially interested in these light blue arrows that point up, which indicate positive vertical velocities or rising air. And at the bottom, we have the dust lifting rate, which we were just looking at to see where the model's lifting dust in the atmosphere. This is a 20-sol rolling average, 20-day rolling average, very much like the CNN's coronavirus 5-day rolling average, rate of vaccinations or whatever. So rolling average here. And it's here to indicate where dust is being lifted from the surface, not necessarily how much, but just where. And this is a cross section along 70 degrees south latitude, which I've shown at the bottom. So you have the eastern hemisphere on the right half of the plot, western hemisphere on the left half of the plot. And we're looking for how dust gets to 50 pascals in the first place. And we're looking at how dust is lofted above 1 scale height. And you can already see that dust is lofted above 1 scale height in the eastern hemisphere, somewhat in the western hemisphere. But I want you to keep an eye on the eastern hemisphere because there's this sort of pluming going on. And throughout the series, this plume will sort of develop and recede on some kind of hourly, daily basis. So the vertical line you see here is where the sun is directly overhead, where it's local noon as the planet turns and local noon goes around at each longitude. So what looks like is happening is you have this pluming in the eastern hemisphere associated with high heating rates of more than 60 Kelvin per day, and a lot of these light blue arrows indicating positive vertical velocities in those regions of really dusty air. The development of the plume looks like it doesn't necessarily depend on it being local noon when the plume develops on that vertical line. It doesn't really look like a diurnal cycle exactly. In fact, the second plume right here occurs around local midnight, and the plume, the good news is it brings dust to 50 pascals really easily and consistently in the eastern hemisphere. It's advected westward over time. These detached dust layers kind of break off from the top, and they rise really high into the atmosphere, above 3 scale heights. And those are advected westward over time and circle the planet usually once before falling out of suspension. So if I just pause at hour 29, for example, we can look at what's happening physically. And what we have is the sun is directly overhead at 130 degrees east, which means that it is midnight at 50 degrees west, where that detached dust layer is. The bulk of the dust is located within 1 scale height of the eastern hemisphere. And it looks like what's happening is this thing called the solar escalator effect. So we have pluming in the eastern hemisphere. This low level dust is at concentrations about 18 parts per million. It's warming the atmosphere, as indicated by these high heating rates, about 60 Kelvin per day. It causes the local environment to become more buoyant, and you see all of this rising motion happening. And dust is raised as that warm, buoyant air rises and is raised and creates these detached dust layers. It also looks like dust becomes more efficient at keeping itself lofted above 50 pascals. You can see that less dust is required to produce heating rates of 45 Kelvin per day than down below. And to prove that the solar escalator is happening, we performed a run in which we turned off the ability of the dust to radiatively heat the environment. So the dust isn't causing any warming in the atmosphere. What happens? What happens is on the left. This is the result of that run. When dust does not absorb solar radiation and it does not warm the atmosphere, then the atmospheric heating follows a subsolar point of the sun, follows that local noon line on the left. There's no pluming. Pretty much all of the dust is below 1 scale height, below 200 pascals. And this creates a pretty compelling case for the solar escalator effect. And the solar escalator was first described for Mars by Dearden et al. In 2015. And they found similar dust lofting processes were occurring in detached dust layers in the northern hemisphere in the opposite season, northern summer solstice. So this effect doesn't necessarily depend on the location receiving direct solar radiation. That's the longitude of local noon that you see going by here. And we see it's not really correlated with that exactly. But it does seem to depend on receiving a lot of solar radiation throughout the day. At the solstice seasons, you're receiving solar radiation 24 hours a day at different degrees throughout the day, but 24 hours a day, because the sun doesn't really truly set at this time of year. So here's a brief summary of what we've learned through our observational and modeling analysis of the B storm. If you recall, we had 2 main questions to answer, the dust lifting and lofting questions. And to answer them, we had to do an observational analysis to see what the B storm really is like, so we can make sure that the model reproduces the B storm well. And what we find is that in addition to creating 50 Pascal temperatures greater than 200 Kelvin, the B storm dust mixing ratios also exceed 4 parts per million at 50 Pascals for most of the B storm in all 7 Mars years that we studied. Dust lofting in the B storm is driven by the dust itself. Dust lifting in the B storm is driven by the cap edge processes. The co-location of surface stresses and dust lifting rates are evidence of this. And our working hypothesis is that the cap edge breeze circulation plays a dominant role here, and it may be augmented by some of those other physics processes I mentioned, like the CO2 condensation flow and katabatic breezes. And finally, dust lofting in the B storm is driven by the dust itself. That is, the radiative heating of airborne dust warms a local environment in which it's suspended, causes the dust to become and the air to become buoyant, and that raises dust into the atmosphere, causing it to ascend over several days and hours at a time. So I wanted to give a brief overview of what we plan to do in the future. One of the main things we want to do is fix the timing and retreat pattern of the seasonal CO2 cap that you saw doesn't really match the observations. Then we want to perform some sensitivity studies to verify the cap edge breezes occurring, that the location of the cap edge matters, and how does it matter? What does it affect? And then we want to implement fully interactive dust lifting and recreate siltation in the model to see how the B storm develops with a more interactive dust lifting scheme rather than the tracking scheme. but I also wanted to highlight quickly what I've already done so you could see. I presented results of the observational analysis almost 2 years ago at the 9th International Conference on Mars in Pasadena. And then I presented the preliminary modeling results at AGU in San Francisco in 2019. And then I presented all of our results at the AGU fall meeting in this last winter in December of 2020. So that's all I have. I'm ready to take any questions that you have.
Okay, great job, Courtney. Although I am biased, it's true. But you know me,
Yeah.
I wouldn't say great job if it wasn't. So we've got about 8 minutes of the seminar hour left over. And at that time, the committee will retire with Courtney for the full grilling session. But until then, let's open up for questions. And I'm not quite sure how to tell who has what questions because I cannot see the Hollywood Squares display.
Seems like Craig has a question.
Yeah, Craig, go.
Real quick, Courtney, awesome job. I loved that presentation, and it was very interesting. So I will not give Bridger any flack about atmospheric circulations on Mars. My question is there an effect of shading on the boundary layer due to the dust? And were you able to look at that? Because if the dust part of the radiation from the dust, from the solar radiation, is heating the atmosphere around that and causing it to loft, wouldn't there be some shading as well underneath that layer and potentially limit some convective boundary layer development?
Possibly. The Martian boundary layer is interesting because it is 10 kilometers deep and Earth is like 1 kilometer deep. And the boundary layer on Mars is really affected by those radiative processes, like you said. So it's actually thicker at higher latitudes and thinner in craters and at lower latitudes. So I'm not really sure how it acts in, a present moment with deep convection going on. But I'm not sure that it would be as affected by deep convection on Mars as on Earth. It's mostly a latitude or a altitude thing, and I don't know if I said high latitudes. I meant high altitudes, like over mountains and stuff, and then low altitudes in craters. So yeah, I'm not really sure about the answer to that. It's also hard to get direct measurements of the boundary layer height, and it's typically thought that the boundary layer is a little bit more shallow at the South Pole at this time of year, probably 3 to 6 kilometers, but it's pretty varied as far as the literature on, how deep is the boundary layer and what exactly affects it.
Okay, great. Well, thank you.
Okay. Somebody tell me if somebody's waving. Oh, there you go.
Yeah.
All right. More questions.
Can I ask one? Tim Wagner, University of Wisconsin.
Yep.
Hi, Dr. Wagner.
Hi, Courtney. Great to see you, and a fantastic job you've done there. I'm an atmospheric scientist by trade, as Courtney knows, and so a lot of what I need to do is to sort of analog what's going on in Mars into a domain that I understand. So forgive this rather elementary question. But we have a unique, well, not unique, but we have a fun time on Earth right around the solstice. It's the only time of the year that the poles receive more radiation than the equator does. And that's a very short period on our planet. You're looking at Mars here, which has roughly the same axial tilt, roughly the same day length, but the seasons are twice as long, right? And so I'm wondering what kind of impact those longer seasons are having on these polar weather type situations.
Yeah, that's a good question. That's kind of what I was looking at answering. It's so, like you said, the South Pole receives constant sunlight at this time of year and for a long period of time. But this B storm is at the South Pole, it really occurs within maybe 20, 30 degrees L sub S, which is something like 30 days or so, 30 to 50 days. And it really occurs around southern summer solstice at the peak. And it doesn't occur before then or after then. And there's no other dust storm like it before or after, but you would think that maybe it would be a longer storm if there was that much solar radiation at the South Pole for that long. So it's interesting that this is so repeatable and it's relatively short given that long solstice period. And I know that in the northern hemisphere, it's an even longer solstice period because of that elliptical orbit. So I'm not sure what it is that matters the most in the B storm. It seems like the sun being up constantly matters, but the sun being up constantly at the height of solstice matters. And I'm not sure why that is. It peaks just before solstice very repeatedly, like within a day or within a half day. So yeah, it seems kind of unusual that it's so sensitive to that solstice period.
All right, well, thank you.
Just to add in there, Tim, remember that Mars is quite a lot further away from the sun. Mm-hmm. So the same sun, so you have a lot less heating available. And the atmosphere is thin. So, there may be some critical temperatures that you need to get something like the escalator thing going. And it's just harder to do that.
Yeah, it's thin, but it's also highly absorbing for the atmosphere that you have, since it's 96% CO2 you said?
Yeah.
Yeah, so that's got to be weird as well.
It actually absorbs more from the surface. Like most of the CO2 in the atmosphere absorbs re-radiated solar radiation from the surface because dust re-radiates at infrared wavelengths, which is way more conducive to CO2 absorbing and warming. So dust is way more radiatively active than CO2 as far as direct sunlight goes.
Oh, well, yeah. Okay. Yeah. Okay,
yeah.
Cool. Thank you.
Yeah.
Do we have any questions from the grad students at San Jose State? Deathly silence.
I will point out that Dr. Haverly just pointed out that Perseverance touched down on Mars, so no crash landing.
Hey, I don't see it on my screen. That's why my head's tilted the whole time. Yeah. Do we have any questions from the NASA Ames group? Courtney gave a practice presentation to that group on Tuesday, and got the thumbs up, so they've heard it before, and I think all of our questions have been exhausted. All right. We've got 1 minute left. Anybody? Last chance. All right. Well, let's give Courtney a hand of applause. Maybe unmute yourselves and let's make some noise about it. Congratulations to Mom and Dad. You should be rightfully very proud. And it's just too bad that you're not local, so we can have a celebration. All right, at this time, Chen Tan, Melinda Kari, Courtney and I will stay on the line, and we would ask the rest of you to log out so we can talk secret stuff. Thank you for attending.
Thank you. Congrats.
Thank you.